Hi everybody, so in this video we compute the Poincare map on a two-dimensional time periodic velocity field. The velocity field we'll be using is the so-called Bickley jet, and we'll be using the time periodic version of the Bickley jet. So the Bickley jet is essentially an idealized flow, which is often used to model interactions in the ocean. So if we take a look at the script, yeah, so here's just like a little description. So we validate the Poincare map on the time periodic version of the Bickley jet, which is an idealized model of geophysical flows. Now, the Bickley jet, so the velocity field of the Bickley jet is essentially derived from the stream function psi, and the stream function psi has two components. So it has one component which just depends on x and y, the so-called steady component, and one component which depends on x, y, and t, the so-called time periodic component. Now, it is important to mention that there are actually various versions of the Bickley jet, and here we'll be considering the time periodic version because we want to apply the Poincare map. Of course, you cannot apply the Poincare map to arbitrary unsteady systems, but you can also apply to periodic systems. The psi0, so the psi0 function and the psi1 function are defined here, and there are a bunch of parameters which you need to take care of and you need to impose. We've chosen the following set of parameters because it is frequently used in literature, so that you can also compare the results with the results from various papers. Now, the periodic period is given by the following quantity. So it's simply 2 pi over sigma 1, and sigma 1 is defined here. And the velocity field needs to satisfy, of course, this condition since it is periodic. So basically what happens here is that every 2 pi over sigma 1, the velocity repeats itself, okay? It is important here now. So if you want to have actually further details, then you can simply click here, and this will open up a new page, which also basically gives the same details of the periodic Bickley jet and shows how to compute the periodic Bickley jet by specifying a bunch of parameters actually. Now let's go back to the main page. So in the main page, of course, here we are dealing with an analytic version of the velocity field, because we have explicit formulas and we can technically evaluate the velocity field at every x, y, so at every point in space and time, simply by plugging the corresponding positions and times into these formulas. Now, since we want to mimic a setting which might occur in an experiment or which might occur from a numerical simulation where the velocity field is not analytic, the way we proceed is we first need to discretize the velocity from its analytic version. So simply what we do is we define a mesh grid, a spatial mesh grid, x and y, and also a temporal grid with the corresponding resolution, where we simply sample points. So we sample velocity fields on this mesh grid. And then once we have the mesh grid, we simply then have the velocity field given on a mesh grid. And then we can simply use the old technique. So we then need to simply define a computation parameters, define a spatial temporal domain over which we want to compute the Poincare map, and we then need to define the interpolants for the velocity field. Then we compute the Poincare map. Poincare map is actually fairly simple to compute. The way you proceed is you compute trajectories. So you basically take a regular mesh grid. So you pick positions, x and y, and you need to learn trajectories over some fairly long time interval. You require this fairly long time interval simply because you want the trajectories to converge, basically, on tori, for example. And then once you've computed the trajectories over this long time interval, you will take the last portion of this time interval. I believe here we take the last 500 periodic steps. And from that, you simply need to sample these points with a period of t periodic. So what you do is you compute trajectories, take the last set of points, and from the last set of points, you sample the points with a period of t periodic. So there is no differentiation, no no computation of the gradients, nothing. You just need to compute trajectories and then sample the trajectories with the corresponding periodic period. This, of course, requires that you a priori know the period, so the periodic interval. So I might just go a bit deeper into the first part, so into the discretization of the velocity field from the analytic data. So here we define simply our functions, psi, psi naught, psi 1, the hyperbolic second hyperbolic tangents. And we then simply need to compute so we then, of course, need to specify the grid, which is done here. Where you can see in the X direction, we have a resolution of 100, in the Y of 100, and the time periodic resolution is 20. So basically, over one periodic time interval, we sample at 20 time steps. Then we define, of course, the mesh grid, the spatial mesh grid. We put all the parameters into this list. So, for example, this U velocity, the Earth's radius, the Lx, Ly, and the epsilons. We then, of course, also need to define a grid spacing for the spatial derivatives, because the spatial derivatives, in this case here, we also need to compute them numerically. And then we simply iterate over all the time steps. And at each frame, we compute the velocity field over the spatial mesh grid. So U and V simply are now on the velocity fields in the exact same form as we all had them. So the first coordinates is for the Y direction, the second one for the X, and the last one for the time. Then we simply need to define a bunch of parameters. Be careful. We need to specify here that the velocity field is unsteady, because of course it is not steady in a strict sense, because it has this time periodic component. So you need to say that this is unsteady. The periodic period is defined here, which is simply, of course, the length of one periodic time interval. Here we then simply need to specify the spatial temporal domain, where you can see we choose to iterate the trajectories over 100 periodic time intervals. So that's simply the time interval that you specify, and then here you simply specify the longitudinal and latitudinal boundaries, basically. And they are not in degrees, but they're actually in kilometers. Sorry. The spacing of the mesh grid. Actually, here that's not the spacing of the mesh grid. Yeah, sorry, that's the spacing of the mesh grid. So we choose basically to have 15. So X and NY are chosen to be 15 and 15. So in total, we have 15 times 15 initial conditions. And we will simply launch the trajectories for these 15 times 15 initial conditions. Then, of course, we need to interpolate the velocity field. This is done using so this is actually the same as in the previous videos. And then finally, we need to compute trajectories. So for the computation of trajectories, again, we take this set of initial conditions and we vectorize it and put it into different batches. And then we basically do the parallel computation of the trajectories. So F-map is simply the flow map, basically. And we compute these trajectories in a parallelized fashion using this parallel F-map function. And the parallel F-map function is simply defined here. So again, what it does, it's fairly simple. It defines initial conditions, and it computes the trajectories for these initial conditions. So that's pretty much it. We then, of course, need to stack all the trajectories from the parallel computation together. And then the last, but actually one of the most important steps, is that we only retain the last 500 intersections of the trajectories with the time slice given by T periodic. So basically, we sample trajectories in periodic intervals specified by this period. So this is essentially what it says. What it does is, okay, here we basically reshape the trajectories into a format where the first dimension is simply the time. The 2 stands for the X and the Y component of the flow map or of the trajectories. And this is simply NY and NX. Actually, I could write this also down if you want. I could write this as NY and NX. This is also, I mean, it's the same thing. It's just that maybe it's clearer if you write it like this. And then you only need to keep the last 500 intersections. So that's what we specify here. So we only take a look at the last 500 intersections. And here we simply discretize the trajectories and we simply undersample. So we simply undersample the trajectories specified by, so spaced by NT, okay? So at every NT steps, we pick the trajectory and sample it. And then once you've done this, you can simply plot this with respect, you can simply plot this where the red dots indicate the initial positions. So these are like 15 times 15 initial conditions. And as you can see, you have various beautiful tori. And this is, of course, done for the full resolution. So by taking all the initial conditions, which compared to the FTLE method or to other methods, they are not a lot. So in the FTLE methods, you need to run many more trajectories in order to visualize the structures. The advantage, that's basically the advantage of the Poincare Map, that you don't need that many trajectories. Now, the disadvantage is that, of course, so first of all, that it can just be applied to periodic systems, and that you need really long time intervals. So the integration here is done over very, very long time intervals. If you choose shorter time intervals, then you will not see such beautiful tori. We've done the same thing also by subsampling, so simply by taking away some initial conditions. And as you can see that as you take away initial conditions, the tori are still visible. However, if you keep doing so, then of course you will get fewer tori until some of them actually disappear or partially disappear. Now with that, I actually want to thank you for your attention, and I look forward to the next video. So here are also a couple of references if you want, actually. This is, I believe, the pioneering paper, so the first paper which introduced this Bickley jet. And actually, yeah, that's it. So thank you for your attention and see you in the next video.